I have a theory about black holes, okay? Hold on. Wait, I need my thinking hood. Riding through the glen. We all know that a black hole has a singularity, which is why it's called a black hole. Then, of course, we all know that near a gravity well, time goes slower relative to the outside of the gravity well. So imagine we had a gravity well. Gravity well? Check it out, it needs some eyes. Just to give you some context. So, I was walking with my wife down the street towards the gym, and it was beautiful. It was a lovely morning, the sun was shining, the birds were singing, the pigeon was spinning. And I said to Cass, hey, isn't it a lovely morning? Can I explain my theory about black holes to you? And she's like, no. So anyway, a singularity, let's just get that in. So imagine we had a universe. What about the well, Simon? Well, the closer you get to the gravity well, the slower time gets, because there's lots of gravity. For some reason, space-time's connected. So imagine we had this line. Okay, this line is the entire universe. I mean, it's a lot smaller. Oh, maybe we could call it a string. Oh, that's my disco ball. So imagine this string theory. This is the whole universe, all right? So you've got the moon, there's the moon, it's the crescent in the post. Then that causes gravity, right? That's the gravity, that's the sound that gravity makes. I hope you realize this. Then you've got the Earth, which is a little bigger than the moon, south and north, and there's Europe, right? And then it does this. Woo! So the gravity is more because it's a well and there's bigger stuff. So then you've got the sun. I can't draw it on the board. Maybe it was like, there we go, there's the sun. That's the edge of it. And it goes like that because there's a lot more gravity because you fall down like, falling down the gravity. But then imagine that you took the mass of the sun, like the stuffness, which the stuffness, that's physics. We'll just get rid of this. Hold on. We'll play the music. So imagine you crammed everything all into the same space at the same time. You know, like my previous video about black holes, okay? So you cram it all into the same place at the same time. All of it. And it's just there. And it's so dense. And it does this to the gravity, and it's really pointy. It's so pointy that those two lines turn into parallel lines. And parallel means that they go in a straight line together and then they never get closer together, ever. So I'll just change that. I don't have a ruler. Oh, I do. The king. So anyway, imagine that that's perfectly straight. And in Cartesianness, they actually be closer together. So maybe like really close together because it's exactly the same point. There we go. But the thing my theory, wait, we're getting to the theory. Look at it. It's like a tiny little hole in the fabric of space-time continuum. This is the black hole, by the way. This is it. This is the singularity because you can listen to it. Listen, see? It's a crotchet black hole. That's what they call them. Because it's a singular, anyway. Point is, time gets slower as well, because space and time are the same thing. Space-time, like E equals mc squared. Because my pen's running out, let's use a different one. This one. E equals mc squared. Energy is equal to the mass times the speed of light squared. So if you took the mass of this, which was infinitely crotcheted, and then you crammed it into the same space, then the mass would be infinite, right? Sideways 8, and then it would be times speed of light squared, which is an infinite number. So that the energy would be infinite, which means the time goes slow compared to everywhere. That I don't know where I was going with that. But singularity, just one. The closer you get to it, the slower time gets. But the point is that it's supposed to be infinitely massful. So it's supposed to weigh an infinite amount. So therefore, the time just stops at a certain point around it. So it never actually forms because time goes on forever. So therefore, because of the event horizon around the black hole, which is why we can never hear the black holes unless they slam into each other, which is the gravitational wave stuff that they learnt with this cool LiDAR detector thingy. I don't really understand. There's lots of lasers. But the waves in space, this is the event horizon, which means that no light can escape because light can't travel fast enough because of that, right? But the closer you get to it, time slows down. So therefore it never existed. And because of Hawking radiation, which we talked about before in the previous video, the quantum foam of the universe can create tiny itsy particles on the edge of the event horizon. And then when they do, they're paired, they're quantum paired, they're pairs. They're little pairs. Look at the little pair. And then one of the pairs is happy and gets sucked into the black hole, but not really because there's no time. So there's time here slows down, right? To nothing. And then this one goes out into the normal universe where we're all hanging out, living in fear and paying our taxes. Then that means that this event horizon shrinks because half of the mass of those two particles that existed in the quantum foam is gone. So slowly over about 10 to the power of 10 to 69, I think it was. Nice. That's 10 with 69 zeros after it. I'll show you. So 10 with 69 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 69! A lot. That means that they evaporate. The black holes evaporate, which means that this number, 10 to the 10 times 10 to the anyway, it's not an infinite number. So therefore, time slows down to an infinite stop. This isn't an infinite number, so therefore, all the black holes will disappear before they're born. Thank you so much for breathing. Remember, be kind, be curious, and stay awesome. And if you want more crazy ideas based on absolutely nothing, come back for more later. On Tuesday at 4:30 a.m, I'll be there. You'll be there. We need a nap.